Howdy everyone, my name is Carson Hanel and I'm from the Texas A&M Internet Research Lab, and I'm super excited to present to you today Vortex, Extreme Performance Memory Abstractions for Data-Intensive Applications. Let's get started. So streaming is a commonly employed paradigm for data-intensive computing. Often traditional streaming applications and software packages are unsuited for extreme performance or rates close to the speed of hardware. Moreover, data streaming continues to offer the same block-based communication model of the 1950s. Because of this, programmers must choose between fast but complex, for example, hand-tuned assembly, and simple but slow, for example, Apache Hadoop, for large problems. Many applications in data analytics, information retrieval, and cluster computing process massive amounts of information. In this paper, we introduce the Vortex programming model, which has the following goals. We'd like to offer a simple abstraction for larger-than-random inputs while squeezing the maximum performance out of hardware. Usually, these are conflicting goals, but we show that this does not have to be the case. Vortex leverages access violations to create the illusion of an infinite buffer in user space. It is by far the simplest to use and fastest platform for various streaming workloads. So let's get into some motivation. So, coding simplicity. Consider the task of finding a user-defined string in a long, for example, 32 terabyte stream of data using strstr. The stream could be originating from a disk, another thread, or arriving in real time from the network. It's usually handled with a traditional block-based solution, which features error-prone pointer calculations, memcopy for data crossing block boundaries, and tedious coding practice, which leads to slow development. Instead, we'd like a much simpler memory abstraction that allows treating streams as infinite. Ideally, this abstraction would provide coding simplicity, no memcopy or boundaries, no error-prone pointer management, the ability to make large, for example 32 terabyte memset and strstr calls, and complete transparency, including thread-to-thread synchronization. So moving on to faster iterator abstractions. Consider implementing a producer-consumer pipeline between threads. Commonly, this is done with iterators. These greatly reduce programming effort by abstracting away error-prone block and pointer management. So let's look further into the read and write functions used by iterators. So here are their internals. Iterators exhibit non-trivial overhead to applications. Writing, for example, requires 3 loads and 3 stores per item, and reading requires 4 loads and 2 stores per item. An optimal solution, on the other hand, requires just 1 load and 1 store per item. Iterators thus unnecessarily stress the L1 cache and can become a huge bottleneck in certain applications, especially memory and data-intensive applications. The desired abstraction would allow memory to be processed uninterrupted, in other words, without boundaries or explicit synchronization. The benefits of this approach include that it requires 1 load and 1 store per item. Dependent upon the CPU, this approach may be 2 to 4 times faster than an iterator. Regular pointers with this approach are abstracted as being infinite, in other words, not actually constrained by physical RAM. And this, overall, could help to maximize application throughput. So now moving on to non-counting in-place partitioning. Consider partitioning in keys across k arrays, for example, during radix sort. The size of each output buffer is unknown a priori, which generally requires a counting pass to pre-allocate buffers. Key movement either requires 2n plus constant memory overhead or needs the slow iterator abstractions that we discussed previously. It is thus desirable to eliminate these constraints and distribute the keys without a histogram pass and operate in place, in other words, using n plus constant total memory overhead. Finally, we'd like to achieve close to the optimal speed with this method. So moving on to producer-consumer abstractions with Vortex. So getting the general idea behind Vortex and its usage of virtual memory in user space, access to reserved uncommitted virtual memory generates a page fault. These faults result in exceptions, for example, segmentation faults, that can be caught by a user space fault handler. We can thus cause controlled sequential access violations in virtual memory. To fix the violation, we map physical pages to the location of the fault in the stream. And once the memory is available, we simply transparently restart the read or write instruction that caused the fault in the first place. So let's take a look at Vortex A, which is our first abstraction. So to avoid faulting each and every 4 kilobyte page, Operations proceed in units or blocks of size B, for example, usually 1 to 2 megabytes. To allow out-of-order reads, let M be the consumer comeback, in other words, the number of blocks by which it can return to reprocess data. Threads are synchronous. The producer is invoked per block within the fault handler. So let's check it out with M equals 1. So we want the consumer to retain the one most recently used block during operation. So down here we've got our virtual memory stream that's reserved to the full stream size for the consumer to run along. So the consumer is given access to the stream, tries to read the data, and faults at the beginning. This fault is caught by a user space fault handler. Within the handler, we allocate block 0, map it into space. We invoke the producer to produce this block. The producer then reawakes the consumer, which consumes this block, and faults again on the edge of block 0. The exact same thing happens. So within the fault handler, we allocate block 1, map it into place, invoke the producer in the handler, which produces the block, and reawakes the consumer. The consumer faults. We're back in the handler again. At this point, because we are more than one block away from the first block that the consumer processed, we want to free it back to the operating system. And this is due to the M equals 1 parameter that we specified at the very beginning. So the idea is, because the fault after block 1 is more than one block after the fault for block 0, we now know that block 0 under the M equals 1 condition can be freed back to the operating system. So this is done, and block 2 is allocated, mapped in place. The producer is invoked in the handler, reawakes the consumer, which consumes, and then faults again at the end. Same exact thing goes on. The LRU block is freed back to the operating system. Another block is gotten, mapped in place. The producer is invoked within the handler, which then reawakes the consumer again, and so on and so forth. And so keep in mind that this essentially lets us, assuming that these blocks are a megabyte apiece, process an entire multi-terabyte buffer with simply 2 megabytes of RAM overhead. So moving on to the drawbacks of this model. So the abstraction is non-transparent to the producer thread, and thus incoming data must still be produced in block size increments rather than continuously. Threads are necessarily synchronous, as the producer is only invoked once the consumer encounters a fault. It never works by itself. Consumer comeback is handled by M, but producer comeback has no such accommodation. So now let's look at Vortex B. In this model, the producer is not aware of the existence of an underlying stream. Instead, the producer writes into an infinite buffer, just like the consumer from Vortex A. This model adds producer write-ahead N, so the number of blocks the producer can be ahead of the consumer, and comeback L, the number of blocks that the producer would like to retain after passing in production. Threads in this model are asynchronous, and this is achieved by tracking and limiting the consumer via guard pages, which cause access violations. This employs the classical bounded producer-consumer solution to track empty and full blocks. So let's see it in action. So the same thing as Vortex A, we've got the virtual memory reserved to stream size, and we're running with consumer comeback is 0, so the blocks that the consumer passes are not reserved. Producer comeback is 0, same thing for the producer. Immediately after passing the block, it's freed. However, we do have N equals 2, and what this means is that the producer can be as much as 2 blocks ahead of the consumer. So let's see how this works. So first, the producer enters the equation, faults on the virtual memory, a block is allocated from the operating system, and then mapped into place. Once it's mapped into place, the producer is reawoken, continues, and faults on the edge of this block as well. Once this happens, the producer installs a guard page to the beginning of block 0 and allocates block 1. This guard page at the beginning of block 0 assures that the first access on block 0 causes an access violation. So from here, the producer maps down block 1 and continues and faults at the end of block 1. At this point, the producer again installs a guard page at the beginning of block 1 and now must wait for the consumer. Because we've specified N equals 2, the maximum amount of blocks that we would like the producer to be ahead of the consumer is 2. So we wait for the consumer to fault on block 0. So now the consumer comes into the equation, faults on block 0's guard page. To be able to process this block, the consumer removes the guard page from block 0 and notifies the producer. Once this is done, the producer can now allocate block 2 because it knows that it is within 2 blocks of the consumer. Block 2 is mapped down. The consumer goes to consume the block that it was given and faults on the very next guard page. Because we have specified m equals 0, the consumer now is going to free block 0 back to the operating system and get stuck on the guard page because the producer hasn't freed it to enter block 1 yet. So here we go. Block 0 is freed back to the operating system, and the producer continues. Once it produces block 2, the producer faults on the edge, installs a guard page, and now block 1 is bounded on both sides by guard pages and is thus safe for the consumer to be able to access. So block 3 at this point is allocated from the operating system because we already know that the consumer is 2 blocks behind the producer, so it can continue. The block is mapped down. The producer continues. The consumer removes the guard page from block 1 and then faults on the guard page for block 2. M equals 0, return the least recently used block to the OS for the consumer. So block 1 is going to be returned. The producer is going to install a guard page at the beginning of block 3, allocate block 4, and so on and so forth. So as you can see, this assures that before the consumer is ever able to access any blocks, there are guard pages bounding the blocks to keep the consumer from entering the producer's space. So let's look at some drawbacks of this model. So blocks cannot be safely consumed until they are protected by guard pages, and thus the minimum distance between threads is the full size of a block. Producer and consumer threads also share a virtual buffer, making it more difficult to isolate them during runtime. For example, forward consumer jumps are not supported. The consumer must necessarily stay behind the producer under this model. And instead of maintaining a pre-allocated stack of blocks, memory is obtained from and released to the operating system during runtime, which incurs a severe performance penalty. So going into Vortex C, our third abstraction. Vortex C further improves upon Vortex B, and it pre-allocates physical memory at the start of the program instead of during runtime. As well, unlike the previous models, Vortex C gains speed by retaining blocks for remapping rather than freeing these blocks to the operating system. Instead of using guard pages to track the consumer, this method uses dual buffers. So threads get separate virtual memory buffers for runtime address space isolation, and blocks are quickly remapped between these streams for producers and consumers. So let's see it in action. So under this, we have m equals 1, so consumer comeback equals 1, producer comeback equals 1, and n equals 1, so producer work ahead. So that's the maximum distance that we like to have between the producer and consumer threads. So the producer and consumer both get their own isolated virtual memory space. The producer's is on top and the consumer's is on bottom. And these threads work asynchronously, so they fault roughly at the same time. And n plus m plus l plus 1 blocks, so 4, are allocated from the operating system. So after the fault, the producer gets block 0 and begins producing it. After producing block 0, the producer faults on the other side of the block. Because L equals 1, we do not free this block yet to the consumer. And so the producer maps down block 1 from the stack and continues to produce. At the end of block 1, the producer faults. Because L equals 1 and 0 is 2 blocks back, we can now free this block from the producer to the consumer stream. So L equals 1, a full block is mapped to the consumer from the producer. The producer gets block 2, and the consumer begins consuming block 0 while the producer produces block 2. They both roughly fault at the same time at the end of blocks 0 and 2 respectively. And at this time, the producer is able to pass block 1 down to the consumer. It grabs block 3 from the top of the stack for itself. The consumer begins consuming block 1. The producer begins producing block 3. And then again, they fault about at the same time. So now, for the consumer, we are an entire block away from the first, and so we can actually begin freeing the first block in the stream. So m equals 1. The consume block, block 0, is remapped to the very front of the producer buffer, so the producer can continue moving along in the virtual space. So let's see this. So block 2 is mapped down, block 0 is mapped back up. and so on and so forth with the vortex. So this is actually where vortex gets its name, from the cyclical motion of the blocks in these buffers. So let's move on to partitioning and sorting. We adapt Vortex to create a novel variant of bucket sort, which utilizes non-counting data partitioning to avoid a histogram pass, and in-place data shuffling to stream sort with in plus constant overhead of RAM. To achieve non-counting data partitioning, each sort bucket is reserved to the full size of input, and the result is the first in-place streaming radix sort, which posts a 2 to 4 times performance improvement over prior work, provides out-of-place speeds with in-place operation. And finally, this abstraction does not require specialized code or memory management to achieve in-place sorting, being instead totally transparent. So let's look at some experiments. Our test configurations from C1 to C3 include 3 different generations of the Intel architecture. So we've got Sandy Bridge, Ivy Bridge, and Skylake X. And each of these are equipped with either a 24-disk RAID or an M2 solid-state drive. So our first experiment that we're going to be looking at is file I/O speed. So this is a read-write test. And what we found was that Vortex C is actually 1.7 times faster than Linux mmap. So this was pretty exciting. And as you can see, we did this with 5 megabytes of RAM, whereas mmap requires 30 gigabytes overhead to process this file. Moving on to the batch producer consumer rate, we compared Vortex to commonly used big data streaming platforms such as Apache Storm and Naiad. And what we found was that Vortex C is 5 to 10 times faster than Apache Storm. And so if you look at this, on the Skylake X, we were able to achieve 65.4 gigabytes per second of throughput, whereas Apache Storm with all cores was able to hit 12.8 gigabytes per second. And this is done while utilizing 1.6 gigabytes of RAM, whereas Vortex just needs 9 megabytes. So now we look at populating an 8 gigabyte vector and throughput in gigabytes per second. When looking at an untouched static buffer, Vortex is 3.1 times faster, untouched as well. And what I mean by untouched is, essentially, once you allocate a buffer, before you actually touch the memory space reading or writing, there are no pages actually put there by the operating system, so it's much slower to process through. So essentially, Vortex doesn't have this downturn. And so then we look at actually faulting in these static buffers, and what we find is that the static buffer is able to reach 28.5 gigabytes a second of throughput, whereas Vortex still reaches the 25.1. So what we see is that we're able to reach 88% of static buffer speed in a pure write benchmark. So now we look at partitioning. The key takeaway is that applied to partitioning, Vortex achieves 92 to 96% static buffer speed, which means we're only losing 4 to 8% speed, having infinite streams that are able to process in place. So from here, we actually look at our radix sort performance, and what we found was that Vortex is actually 2.9 to 4 times faster at sorting 8 gigabytes than the nearest in-place radix sort competitors. Moving from there, at sorting 24 gigabytes, Vortex is still 2.7 to 3.1 times faster than the nearest in-place radix sort competitors. Moving now to the fastest out-of-place radix sort, which we consider to be in a separate league from Vortex, as they require 2n plus O of 1 overhead, whereas Vortex requires n plus O of 1. We still manage to have a 1.6 to 1.9 times improvement in speed at sorting 8 gigabytes, and keep in mind that Vortex can still sort twice as much data at this same speed. So, thank you, and I hope that you enjoyed this presentation. I wish all of you a wonderful and fruitful ASPLOS, and if you have any questions, please ask me on the Slack channel. I would love to answer any questions you have, or if for any reason that you can't participate in that discussion, please contact me at carson@cse.tamu.edu, and let's figure out how Vortex can work for your application. Thanks so much.